Ooh, everyone. Let's talk about related rates. What are we doing today? So, interrupt me when you have questions. But here's how I kind of define this stuff. And this is some of my old notes. Oh man, why does that not look like it fits well? Oh, it does fit well. So, a few things when we're doing related rates, we're actually doing like the real problems, related rate story problems. You have to do this on the AP test. They're usually like free response questions, but they're also multiple choice. I mean, this stuff's going to be on there. And I'm going to demonstrate a few examples of this. The Khan Academy stuff actually kind of breaks it down better. Like, they break down into like, oh, just identify things that you know, identify the expression. But I'm just going to do this as one big problem. So there's a procedure for this. If I were to define this in related rate story problems, the idea is to find a rate of change with respect to time. So with some time of one quantity by using the rate of change of a related quantity. So you got to find rates of change of quantities. And it's going to be like, if our quantity is y, you end up having like the dy over dt or dh over dt. Now, a lot of times over dt, where t represents height, this, or t represents time, and this can represent, maybe h would be height. Maybe you see dv over dt, which is v is volume, or dA over dt, if it's area. Whatever our variables is here, we got to differentiate at some point to find the rate of change. So whenever I find rate of change, I'm thinking derivative, d something over dt, whatever that something is. All right? So a lot of this is about figuring out what are my givens, what are my equations. At some point, I'm going to derive something. And I'm going to use that implicit differentiation. So here's the trippy thing with all this, folks. Let's say I have this equation, y equals 3x squared plus 1. If this is my equation in here, and I have to differentiate this with respect to time. So I'm doing it differentiate with respect to time right there. I don't just say, oh, dy dt equals 6x. That's incorrect. You are deriving everything with respect to t. So you have to like chain rule the d over dt. You know how we had to do chain rule the dy over dx for implicit differentiation? You're going to have to do that for every variable. So what we have here is we have dy dt equals, derivative of this is 6x, but then times dx dt, and then plus 0. So always think you're going to be doing the whatever over dt at the end, d over dt part. And that's the part people forget. So key things to do, steps. You like steps? I like steps sometimes. Step number 1, I would draw a figure if necessary. Sometimes it says, oh, there's stuff being poured into a silo, or something's coming in and something's coming out. I like to draw a picture of this if I can to help me visualize it, or if it's some kind of shape. To me, that helps. And then you can label things. And also, sometimes you might need to choose variables for unknowns. So if it's talking about height, maybe I call it h for height. If I'm talking about width, maybe w. I don't know. And then I might want to write those out. And then write what is given and what is to be found. So what is given to you? Sometimes like rates are given to you. Sometimes equations are given to you. Sometimes like it's just the actual variables are given, whatever. Write out everything that's given to you. And then step 3. So write an equation relating to variables. So, and I think that's part of step 2 sometimes. And it's just write everything. Is there an equation related to this? Are we talking area? Sometimes like I give you the equation. Sometimes I say, hey, we're talking about area of a square. I can't write at all. Well, I don't have an equation for area of the square, but I know area equals side squared would be the area equation of a square. So I might write those out. All right? Now, a few notes when you're writing out equations, and this is kind of like intermediate level stuff. If the quantity is changing, it must be represented with the variable. Like, so think about like all those quantities. Sometimes if you know something's going to be changing, like is the area of the square getting bigger? Then area and then the sides of the square should also be bigger. If a quantity is constant, you can just put the number right in. So sometimes you have problems like, oh, I have 500 feet of fence and I need to make a rectangle shape that has the greatest area. What are the sides of my rectangle going to be? Well, the amount of chain link fence is probably constant. Like I have 200 feet. So that's something you don't need a variable for, but you'll need a variable for the sides. So that's kind of intermediate. That's kind of like intermediate level stuff. Other thing is you have to look for secondary relationships. So maybe it says, oh, that chain link fence, the width has to be 2 times the length of the fence. So that would be like a secondary equation to put in. And then at some point, you're going to combine some equations and then you're going to derive with respect to time. So d dt. You'll substitute numbers in after you derive and then you figure out your answer. As long as you know what you're given and what is supposed to be found, you can kind of get to the path you're going. That's the way I think about this. And a lot of this is just going to take some examples. I think you really have to do some. So, here's my explanation of all this. I said some of this. In implicit differentiation, you chain a dy dx. Related rates, we chain a d over dt. And you got to figure out your variables and equations and figure out what they mean. This part about most variables are changeable. So we'll have this. And the certain things are constant. And if I use, like if you're trying to figure out what variable it is, if I say the rate of change of the height, then that's going to be like a dh dt as your variable. Oops, you can't even see that part. That's going to be a dh dt. There. So think about all those things as you do this. Let's try some example. So this is a basic example. Sometimes I'm just giving you all these things and I say, find dy dt. All right. I'm given this, and given this. So I like this could be a word problem, but I'm giving you all this information. We got to find dy dt. Well, I got this equation, x times y equals 12. Cool. Well, what I can do, since I already have my equation, I can derive this one. So I'm going to take x times y equals 12 and derive this with respect to t. What happens when you do that? Product rule this thing. This is going to be, the x is going to be 1 times dx dt, or just dx dt, times y, plus x times dy dt, that's the derivative of y, equals 0. And you got to solve for dy dt. Well, I'm going to plug in what I can. Dx dt equals 6. So I'm going to plug in 6. And then, yes, -6. Yes, it is, -6. Perfect. And y equals 4. So I'm going to plug in times 4. And then x. Oh, what is x? I don't know x. However, this is the part where I can use equations to figure that out. If y equals 4 and x times y equals 12, x has to equal 3. I can plug in a 3, and then I don't know my dy dt, so I just write dy dt equals 0. Now that I've plugged things in, I can solve for dy dt. dt, you add 24 to both sides. And so then dy dt, would equal 8. There I go. There's no units in this case, so I'm not worried about it. So that's the idea. I got my equation. I was given some givens. Differentiate with respect to time, because that's what I know, because I have to find dy over dt. You plug that in, and you'll be good. All right. Let's try something else, though. Okay. Word problems. Gosh, I hope I can do this. I haven't done this in a while. A windlass. A windlass. A boat. A boat. Is used to tow a boat. Oh, what is a windlass? Oh, it's just like a thingy right up here. That's not even the whole boat. Never mind. I don't know what a windlass is. I hate when I use this. It's used to tow a boat to a dock. The rope is attached to the boat. So you got like this on top of a hill. Rope is attached to the boat at a point 15 feet below the level. Oh, a windlass is used to tow a boat to the dock. A rope is attached to the boat at a point 15 feet below the level of the windlass. So this is the rope. It's attached right here. It's like the top of a pole or whatever. If the windlass pulls on in rope at the rate of 30 feet per minute, at what rate is the boat approaching the dock when there's 25 feet of rope out? So, okay. I look at this and go, what do I do? Well, I know a few things. I got this triangle shape. Okay. I know that this is the rope, and we're going to call this Z. Right? And then this distance here from the boat to the windlass is going to be X. And this is 15 feet tall. They've already made the shape for me. All right? Now, what else? I know. I have a few other numbers in here that I want to use. So they already used 15 feet below. That's already used. Check. Right there. And then what else do I know? If the windlass pulls in rope at a rate of 30 feet per minute. So something is 30. And I know it's a rate. But I'm not sure what that is. It pulls in the rope. That means the rope is coming in. Well, the rope is Z. So I can say DZ. DT is 30. At what rate is the boat approaching the dock when there's 25 feet of rope? That's when Z equals 25, since Z is the rope. Now, the question it's asking me, what rate is the boat approaching the dock? So I have to find some d over dt. Well, the rate it's approaching the dock would be this. The dock would be like right here. So we're looking at dx. It's the rate that this is changing because the rope's pulling it in. It should get closer. So again, when you're doing these things, like sometimes I don't even know what I'm doing with these problems. I think the first part is to try to write every given thing you can with this. I wrote some variables down. One thing I don't have is an equation. And you're like, you get stuck. Because they didn't really tell you one. But they gave you this shape here. And what is this shape? This is a right triangle. And this is a classic case of using the Pythagorean theorem. And you know the Pythagorean theorem is a squared plus b squared equals c squared if you have a right triangle and the legs are a and b and the hypotenuse is c. We have a right triangle here. So my equation could be x squared plus 15 squared equals z squared. There we go. Now that you have an equation and you have some givens and you know what to find, I'm just going to differentiate that and go. Oh, that's my equation to differentiate. I got D's and Z's. So I derive this. Let's say I try to find D of T of X squared plus, that's 225, equals Z squared. That's going to be 2x dx dt is equal to 2z dz dt. All right. I'll plug things in. I get 2 times x. I don't know my x right now. 2 times 25 times 30. What's my x? And I don't know this, but I know I can plug things in because I know z and I know this. So I'm going to say my x squared plus 225, that's 15 squared, equals 25 squared. And you might not know 25 squared. So you do it on a calculator and you get 625. All right. Subtract 225 from both sides. Get x squared equals 400. And the square root both sides. Now, this is a weird thing where x is going to be plus, now square root of 400 is 20. So plus or minus 20. Now, so you have to consider both. I have plus or minus 20. This is where sometimes you have to use like a reality check here. Could it be negative 20? Not in this case. Because we're dealing with positive values, positive distances. Negative distances would be like if it's already negative distances wouldn't make sense. So we're just dealing with x equals 20. So there I go. Plug that 20 in. And then we're just going to do some math right here. I'm going to move that down a little. Oh, I can't. Doesn't work for me. Huh. Oh, well. Hopefully you can see it still. 40 dx dt equals 2 times 25 is 50 times 30. Going to be 1,500. Divide both sides by 40. I think that's 1,500. So I'm going to do my work up here because I don't know if you see the bottom. Dx dt is equal to 150 divided by 4 if you reduce. Now, so there's my answer. I could do it in decimals if I wanted to or whatever. But what are my units? I have feet and I have minutes. So going back to what we did like last time a little bit, like everything's either in feet or minutes. You have like your distance on the top and your time on the bottom. Since this is a rate, this is going to be feet per minute. A sentence explaining this means I would say the boat is getting closer to the shore at a rate of 150 over 4 feet per minute. Something like that. And you're good. It's kind of weird. Questions? We'd be like, I'll watch the video later. Me too. The croissant? Jimmy Neutron memes. I don't know Jimmy. No, I'm not hip with Jimmy Neutron. I don't know who that is. No, he's a cartoon. 3-dimensional cartoon. Okay. Let's do another one of these. I got so many of these. I don't think I'll do them all, though, because I think I'll... A policeman is traveling south. Is referencing policemen in 2020 appropriate in math problems? Canceled. Let's do the other one. Okay. No, actually, I think I like that one. Oh, well. Should be a police person. Oh, well. Old times. I like this one. There's directions. So, policeman's traveling south toward an intersection, spots a speeding car traveling east away from the intersection. Gosh, there's so many jokes we can make. When the policeman is 0.6 miles from the intersection and the car is 0.8 miles from the intersection, the policeman's radar shows the distance between them is increasing at a rate of 20 miles per hour. The speed of the police car is 60. What is the speed of the car? All right. So if you got a problem like this is where, man, sometimes you need a good imagination. What's going on? So towards an intersection, let's draw an intersection here. Intersections are going to be like two roads. Like that's, so imagine these are two roads. And the intersection's right there in the middle. Now, a policeman's traveling south. So we're going to say south is down because that's how it works, right? So this is the policeman, P. He's traveling down and spots a speeding car traveling east away. East in this case would be going right. Spots a speeding car. We'll say S. East away from the intersection. When the policeman is 0.6 miles from the intersection and that car is 0.8 miles, the policeman's radar shows the distance between them is increasing at a rate of 20 miles per hour. What is the distance between them? That would be this line. That would be the distance between them. All right. What is the speed of the car? All right. So we got an intersection. Policeman's going towards, this guy's going away. The distance between them is increasing. So let's call this distance right here. What shape do we have? We have a triangle again. Oh, man. Triangle. Let's call this side P. We'll just call this whole side P and this whole side S. And let's say P is the distance the police from intersection. My handwriting's really bad on this. Khan Academy does a better job. I don't know. Things don't pick up. And est is distance, the speeder from the intersection, right? So, and then we have this total distance. Let's just call this D. That's the distance between, right? So when the policeman is 0.6, so our given, P equals 0.6. And the car, that's actually 0.8. So S is 0.8. And the distance is increasing at a rate of 20. So, I hate using D because it's like DD. Let's not use D because we're already using that for derivative. Let's go distance between. Let's go B for between. DB, DT is going to be 20. If the speed of the police car, so that means is 60 miles per hour, so dt equals 60. We want to find ds dt, the speed of the other car. All right. We got a right triangle. My equation I can write is p squared plus s squared equals b squared. Right? Okay. Well, let's figure this one out. So if I derive these things, I'm going to derive both sides. Get 2p dp dt plus 2s ds dt equal 2b db dt. And I would just start plugging things in. Obviously, I'm going to need more information. I think you guys can see that. So I'm going to get 2 times p and times 60. So there's a problem here. I'll point it out later. Nope, 2 times 0.8. And then I got to find ds dt equals 2 times b, which I don't know, and then times 20. Now, one thing we didn't deal with in the last problem is negatives. The car is, this police car is 0.6 away. This is 0.8 away. But when I say the police radar shows the distance between them is increasing at a rate. Okay, when it says if the speed of this police car is 60 miles per hour, but the police car is going down, that means this P is actually going to be shrinking because he's going south. So what we actually say right here is that's actually going to be negative. And this is one of the other tough things to watch for. And I think this is going to matter. This might matter. Might not. But we should watch the negatives and positives. And is that going to be negative? Is that going to be positive? I actually don't know if it matters for this problem. I think it does. It does actually, I think. You just got to watch how it's written. Now, I got to find B, right? Well, I can use, to find this thing, I can plug it into this equation. So I get P squared, or I get 0.6 squared plus 0.8 squared is equal to B squared. Now, that's a calculator time here, folks. And you can do all the calculator, but you know what you're going to get for B? You are going to get 0.1 for B. You plug that in. Now, I want to teach you a trick right here. I hope you're paying attention. I'm going to save your life. You ever heard of a 3, 4, 5 triangle? Right triangle? Yeah. Yeah. So it's a very common right triangle, 3, 4, 5. 3, because that 3 squared is 9, 4 squared 16, that's 25. That equals 5 squared, right? These are one of these Pythagorean triples. Well, 3, 4, 5 is a right triangle. Also, 6, 8, 10 is a right triangle. You can just double it, and that'll always work out, as long as these are proportional. So what we actually have here, and now you got to plug this into a calculator, folks. You could have done it this way. But we have a 6, 8, 10 triangle right here. So that's how I know B is 0.10 or 0.1. So It's a little shortcut you can look at later. But 0.1. And B, yeah, we're good with that. And the car is speeding away, so I know it's going to be positive 20. All right, so we do the math here. Ugh. This is going to be 1.2 times negative 60, which would be negative 72. Yep. 12 times 6 is 72. Plus 1.6 ds dt. I'm probably going to want a calculator at some point. 0.1 times 20 is 2. 2 times 2, that should be 4. And now I'm going to add 72 on both sides. 1.6 ds dt equals 76. Divide by 0.16 or 1.6. See, this is the part where I'm just going to pull a calculator out. These take so long. I'll make you guys do one next time. Oops. Sure. I'm going to leave it as a decimal. I'm just too lazy to do anything more. ds dt was 47.5. Now, what are the units of that going to be? That is going to be, it's a rate, and I'm dealing with miles, mph, miles per hour. So miles per hour. That's the speed of the car. So what does this mean? Speed is an absolute value velocity. So what would have happened if I would not put a negative right there? That would have been a wrong answer, yeah. It would have been off. Yeah, because you would have subtracted 72. Made it completely different. Yeah, so that's why you gotta watch the negatives. So the speed of the car is 47 miles per hour. 47.5 miles per hour. It's going away at that speed. All right. That's all I'm going to do for the example.